figs, or we'll call them significant figures, these are used for consistent results from measurements. Believe it or not, when you see a number in the scientific community, just the number itself indicates how precisely it was measured. And they follow these 4 simple rules. These are the rules we are going to follow for pretty much any number for the rest of the year. These are very important for you to ingrain. The rules are provided for you on the reference sheet, but you need to know how to use them at all times. That is the expectation. So let's take a look at these rules pretty quickly. Non-zeros, always significant. Your numbers 1 through 9. Zeros between non-zero numbers are always significant. So that means things like we see the zeros between non-zeros, right? Or there's the one down here. Zeros between non-zeros. Okay? You don't need to know the order of the rules. I'm not going to quiz you on what's rule number 3. We're just using these sig figs as we have them. Leading zeros are never significant. They're only placeholders. So leading zeros, what I mean, are the zeros to start a number. All of these 4 zeros, not significant. I don't have any other examples on this one. Trailing zeros are only significant if there's a decimal. Again, this shows the precision of the instrument. So at the end, this would be on a very precise scale that measures to the, 10,000ths place. Unlike if it just said 8.1, that would be a very low precision scale, something you might have in your house. Again, this 0 at the end is significant. It's showing how precise that measurement was. Again, 10.0 at the end. We see in this one, with 3 million, there is no decimal place. So that indicates that all these zeros at the end are just placeholders. This would be the example like I went outside and I saw about 3 million people today. The precision of that measurement is so imprecise, you really can't say it with any significance except for the 3 portion, which again, in that example, I don't think you'd even be able to say that to be very precise. So these rules are just the first step in knowing what to do with numbers in chemistry. All of these are related to measurements. Any number you see, imagine it being related to measurements and how it was measured. Please come in with any questions you have about these rules. Alright, so depending on what we're doing with these, we have different rules. Addition and subtraction, same idea. So when we look at addition or subtraction, lowest significant decimal place, that means lowest place 10,000ths, hundredths, and so on. So if we look at these numbers, this has it to the hundredths place. This has it to the thousandths place. This, no decimal, has it to the tens place. So the lowest that they all have in common would be to the tens place. Now if we were to add these up on a calculator, your calculator does not know sig figs. Humans do. So you would get originally 131.451 grams. But that, that is not to significant figures. We see that this would be rounded to the tens place because that's the lowest that they have in common. I know these numbers don't have significant figures in the tens, but none of these have it to the thousandths or to the hundredths. So I look at my tens place, that's a 3. Because there's a 1 next to it, that's not going to round up the 3 to a 4. That'll be 130. Again, no decimal place, grams. So even though we added 2 other things to it, based off the very low precision of the 130, we can't say with any confidence that it would be anything higher than 130. Unlike this, what we have in the subtraction, we have the tens place and the tens place. So that means our number is going to be rounded to the tenths place. So when we add this up, or I should say subtract this in our calculator, we get 2.58 grams. So tenths place is the 5 because we have an 8 next to it. That's going to be equal to 2.6 grams. I strongly suggest that you line up the decimal places like you did back in elementary school, because this will help you visualize what your rounding space will be. Don't just accept the way it's provided. make it so it's easy for you to be successful with. All right, let's look at another type of math we do, multiplication or division. Lowest number of sig figs in any number used in the calculation. So with this, we'd want to evaluate how many are in each. I've got 3 sig figs here, 2 here, and 1 here. If you're not sure how I came up with those number of sig figs, look back at the rules and apply them to these numbers. Now my units are going to be centimeters cubed, because centimeters times centimeters times centimeters is centimeters cubed. My original number would be 1.215. That'd be from the calculator, but I only have one significant figure, so I need to round that to the, in this case you look at the left side number, so this would be one significant figure. Because there's a 2, I can only say that with confidence that this would be 1 centimeter cubed based upon the very imprecise measurement of the 0.002 centimeters, only one significant figure. It may not make sense to you now why this is true. Don't worry about it. What we're here to do is apply the rules as stated. Another example down here is division. I've got 3 sig figs in this number, 2 here. So of course my units are going to be grams per milliliter. No naked numbers, they're all dressed with units. My number from my calculator is something like 197.0588. My answer can only have 2 significant figures, so that would be 1 and 2. However, because this is a 7, that needs to be rounded up. And if I try to write 200 like this, well, that's 1 sig fig. If I put a decimal, that's 3 sig figs. This is where scientific notation comes in handy because it only shows the proper number of significant figures, yet would have the same value of 200. So this would be 2 significant figures, because that's what's in the decimal, and 2 times 10 to the second is 200. Now another type of math are what are called conversion factors, where we start off by a value, measured, calculated, whatever, and we convert that to a different number with different units, but they are equal in value. This really manipulates the idea of the identity process we'd find in math, where something times 1 times 1 times 1 times 1 equals the same value. The thing that's usually hard for students to get is they don't realize how fundamental this is to chemistry. So I really want you to follow along. This is just involving sig figs. We'll do conversions in another lecture, but I wanted to show you in action here. So we're looking at converting this amount of money, 230.50, and we want to convert it all the way to nickels. So I'm going to put that all the way on the other side. No abbreviations on this side. We'll use symbols and stuff later on. But the idea here is that we're multiplying it by a ratio that's equal to 1. So I know there are 20 nickels in $1. Right? You guys know that, hopefully, if you've had enough interaction with money. So this is an exact value, not a measured one. It's kind of a man-determined one, or a man-accepted one, or woman-accepted one. The idea is that we accept it as true. It's not a measurement. So there's no role in sig figs with this. It's only what is measured. This is a measured value. Right? You had to count it out. You had to determine it. So when we do our math here, we need to see that there is 1, 2, 3, 4, 5 significant figures. So when I multiply this over here, I get 4610, I think on the calculator, but I need 5 sig figs. That would make it 4. And it feels weird to put the 0.0, because it's like, well, I can't even have a fraction of a nickel, but just roll with the concept of the rules. Don't fight logically with it, just roll with the rules. Another example down below, some metric system stuff. So 50 milliliters, and I want to convert that to liters. So again, there is a ratio. You would see that there is 1,000 milliliters in 1 liter. This is where units will cancel out. You'll go into that for the next lecture, I believe. So again, I only have one significant figure. So when I divide that, I get 0.05 liters. Again, I start off with 1 sig fig, I end with 1 sig fig. What's in the middle is exact. It's not a measurement, so no sig fig manipulation or roll in it. We'll go in that, and I'll remind you that numerous times in the following lectures. All right, let's take a look at scientific notation. By this point in time, you've used it a little bit in math, or a lot of it, but this is science. This is where we use scientific notation. This is our zone. Now remember, in the previous couple slides, I talked about 2.0 times 10 to the second. This is where it's used to illustrate precision. We could use this solely throughout the rest of the year and not use regular numbers at all, but I think that would be a little tedious for me and for you. Now, one thing that often messes up students is it a positive n or a negative n, meaning the exponent? Another way I remembered it, I finally got it down, I think in college, is that when the standard number, 75,000, is less than 1, then n is negative. Okay? When the number is greater than 1, the n is positive. So like I said, 75,000 is greater than 1, so that would be a positive n for how many decimal places it's been moved. And likewise, if I had, 0.1, that number's less than 1, it's going to be a negative n. That seemed to help me out. Hopefully it does for you too. So, examples, you again see that there is, get a little closer look here, 1, 2, 3 sig figs. Again, if you're not sure why there's 3, look back at the rules. They're very directly placed that you need to know and apply. Again, 1, 2, 3. The number is greater than 1, so it's a positive exponent. Likewise here, 1, 2, 3, 4 sig figs. I see my 4 sig figs here. Number is greater than 1, positive exponent. Leading zeros, not significant. Only ones are right here, 1, 2. Less than 1, negative exponent. Same holds true here. All those leading zeros, not significant. We've got our zeros here. Uh-oh, looks like I forgot a 0. Whoops. Got a 0 in there. And to the negative exponent. You'll need to be comfortable going back and forth between the two types. We'll use them when we have to. That's like we're using large numbers with the number of molecules or atoms or protons. We have these big numbers that are in scientific notation. Or you might have very minute amounts, milligrams, micrograms of things that are going to be small. So get used to using them. Again, you see the decimals always between 1 and 10. No 10.97, 1055 times 10 to the third. That doesn't fly. I don't care if it did in math. That's not scientific notation. That's just wrong. Come in with any questions, and I hope to see you soon.